Hello everyone. The topic today is BGP, external routing. And as this figure is suggesting, this is, I don't have the usual pointer, this is self-organization. The internet at a global scale is not run like OSPF, like we saw in the previous lab, but something less structured that relies on BGP. And we will discover this today. So the topic is called inter-domain routing. Why is it invented? Why don't we do OSPF or something similar, RIP or globally in the internet? Well, there's at least two good reasons. The first one is certainly scale. The internet is large, and that would not scale. But there is a more subtle reason. The internet is heterogeneous. There is not one company that's running the internet. Nobody is running the internet. The internet is the collection of operators that agree to work with each other and provide internet service. So there is no way they could agree, for example, on the weights that you give to every link, because there is no global organization between at the world scale. A bit of terminology. Routing protocols, like we have seen so far, are called interior. It means within one domain. EPFL, Swisscom, AT&T, each of those companies run their routing protocol. They have a management team that surveys what happens and supervises all the decisions that are taken. So you can run, for example, OSPF with multiple areas. That is what is done in very large single company networks like AT&T's network. Between domains, between companies, we use exterior routing protocol. Now the good news is exterior routing protocol, there's only one, and it's BGP version 4. Some others have been published and beta tested, but only one is deployed, for reasons that are similar to the difficulties we saw in deploying anything else than IP version 4 in the internet. We see that moving from IPv4 to IPv6 is very slow and very complicated. Similarly, moving from any exterior routing protocol to a new version is something very tricky and very difficult, which is not happening and probably won't happen soon, other from minimal updates. So today, or for us, exterior routing means BGP. BGP stands for Border Gateway Protocol. A bit more terminology, two terms that mean practically the same thing, and in practice for us they will mean the same. A domain is called an autonomous system, or also an autonomous routing domain. For most people they are synonym. There is a subtle difference. Every AS, every autonomous system, has a number, a 32-bit number, which is not an IP address, although it has the format of an IPv4 address, but it's the number of that domain. In BGP messages, we will need, as you will see, we will need to describe paths, so we will need to have numbers for identifiers for domains. So this is done by, as usual, a number. There are also private numbers, so those numbers this range of numbers is private AS numbers. We will see a use of it, similar to the private IP addresses. If you have a very large network, you might use BGP to run it between its multiple components, in particularly large conglomerates or companies that are made of subdomains that are historically coming from different companies may use BGP inside their own domain using their own private numbers here. An ARD means an AS that does not have a number. Practically, this is weird. Why would an AS have a number or not? We will see why. ASs that do not have number, ARDs, are domains that are connected to a single provider. EPFL, for example, is an autonomous routing domain, but EPFL does not have an AS number, because EPFL is connected to the rest of the world via switch. And switch has an AS number. So for the rest of the world, EPFL is behind switch. We found this concept already in OSPF when we had the concept of stub network. A stub network is a network that's behind a router, And when we computed shortest paths, there was no need to compute the shortest path to all the stub network. All we need was to compute the path to the routers, and then once we're in the router, we know how to go to those networks. It's the same idea here, to simplify the scale, to reduce the number of autonomous systems that exist in the world. Those that are stub, that are just behind a single AS, they don't need a number. So that's the small subtle difference. But in this course, and like in practice is done by many, I will use AS for a domain even if it does not have a number. Although strictly speaking, we should not. Here is a picture that shows how all those things fit together. I'm showing 4 domains. One of them here is a large domain that runs OSPF. Inside OSPF, as we know, there can be multiple areas, but all those areas are inside the domain. For BGP, there's no difference whether you have OSPF with one area or multiple areas or something else than OSPF here. So we see that routers between domains communicate by using BGP, and inside the domain they communicate by using their routing protocol. And we see one difference between OSPF area principle and the organization that exists in the world, which in some sense is similar to the problem we had with OSPF. With OSPF, we make a large number by taking areas and putting them together. We can view the internet as using the same trick. We have a large number of domains that are connected together. The first difference is that with OSPF, there is one BGP router at both ends of the boundary between 2 domains. So when 2 domains communicate, they each have their own BGP router interconnected by something, which in this figure is a connection, a communication link here. Whereas with OSPF, we know that a border area router sits on both areas. Right? It can be made a bit differently, but that's the principle. And the reason is very simple. When you have 2 companies that agree to work together, usually they don't agree to have a common router. I mean, who owns it, who runs it? You don't want to have that kind of problem. So everybody has their own router, and then they connect to each other. So we want to minimize the number of friction points by minimizing the things you need to have in common in order to communicate. BGP will use the method of path vector, and we will see that this in particular enables the use of policy routing. Those are the 2 keywords we will now discover. So path vector is very simple. If we compare to OSPF, with OSPF there was the concept of link costs, and with OSPF we are computing shortest path. With BGP we will not be doing that because we don't know what value to give to links. Even if we would know, we would not be sure. We use the same scale. So instead, we use an explicit description of the paths, which is very verbose and very long, but this is what is done. For example, here, assume a domain A has 2 network prefixes, N1 and N2. It informs its BGP neighbors through BGP. We'll see the details in a few minutes, how this is done. And it informs it by giving the complete path. So the path here is the AS number, A, followed by the network prefix. So B will receive this, and B will, if B decides, will inform E of the existence of N1, N2, and the path to N1 is AB, or if we use reverse ordering here, BA. So when E receives this, E knows that network N1 is reachable via a path that goes through the domains A and B. Here. Similarly, E may have received another path from the succession of domains C and D, for example. It may have received for N1 the path DCA. So now E has 2 paths, for example, to the network N1, the path BA and the path DCA. One of the principles of BGP is that E will choose one of them. Which one? We don't know exactly, and we will see that there are many rules that allow us to do a certain choice. For example, here, if B uses a very simple rule that says I use the path that is the shortest in number of ASs. So, for example, to go to A1, I have two paths, one that uses 2 ASs, another one that uses 3. If B applies this rule, it will keep only this AS path here. But you might choose other things. For example, E might have a reason to not like B. Why? Well, for political reasons. B and E are in countries that are not in very good terms, so they don't want that the traffic transits through this unfriendly neighbor, for example. Or the link between E and E is very expensive. It's a telecom link for which you pay a huge amount of money, so you want to use as little as possible of this link so that you don't pay a lot for its usage, or you don't have to upgrade it to higher capacity, or whatever other reasons. This is called policy routing that we will see in a detail here. But before going to policy routing, let's go to the difference between what is called external BGP and internal BGP. This is causing a lot of confusion when you read in the internet on blogs and forums, people that are asking questions are trying to configure their BGP network. So they want to do Lab 6 without having taken the course, then they come into this confusion here. BGP is an external protocol, but for some reason there is an internal version of it. What is it? Well, it is simply due to the fact that if we zoom on this domain here, domain D3, here I'm showing 4 routers, C, D, E, F, that are using BGP because they speak to outside domains. Now, when C receives some information from D1, it needs to pass it along to D4 here, but C is interfacing only D1. So of course, we don't have a single router that interfaces all of the outside, although that can be done in some cases, but in a network that has a certain size, that will not happen. So we need a mechanism for the different BGP routers to pass the information to each other that they have learned from each other. So you need an information dissemination protocol inside the BGP routers that are inside the domain. This protocol is BGP also. You find a classical thing that's done in computer science very often. You try to use the same mechanism for multiple purposes if you can. So this dissemination of information, which could have been using different things. For example, we could have decided to put all the BGP information into the OSPF table. OSPF, you have a database that can describe everything you want about your network. So we could have decided that C, for example, takes all the information it has, puts it into OSPF, disseminates it via OSPF, and E would learn it from OSPF. But this is not done. Partly because OSPF, the success of OSPF is relatively recent, although it's an old protocol, but it's only recently that many, many networks have OSPF, or that it's dominant. So there is not a single interior routing protocol. So this is, BGP decided to do it its own way. So BGP distributes, and it distributes it using the same protocol BGP as is used between external peers. We put an E to say that the peers are external or the peers are internals. Right? Other than that, eBGP and iBGP are the same with 2 minor but obvious exceptions. The first exception is that what do you do with the AS path? So obviously when you pass a route from C to E, the route is not, when you pass the route from B to D, then the route had the prefix D2. Now we are in another domain, so we add the AS number of this domain to the route. This is the natural thing to do. This is what was done here. When C passed the information about the route it had received, it had added itself, C, to the path. This is how the path is discovered. When we are inside the domain, we're inside the same domain, so we don't add an AS number. That's obvious. Something a bit less obvious is that the routes learned from iBGP are never repeated to iBGP. So when C learns a route from A, it needs to repeat it to E, for example, but when C learns a route from D, an external route from D, it will not repeat it to E. Why is that? Because we make the assumption that there is what is called a full mesh. all BGP routers inside one domain can speak directly to all other BGP routers inside this domain. And the default way to do that is to establish a TCP connection with all the other BGP routers inside the domain and exchange the information inside this domain, like is shown here. For example, C can establish a TCP connection via F that goes perhaps via an intermediate router R that is not speaking BGP, is a normal router that doesn't speak to the outside. And this is what gives rise to what is called a BGP mesh. We will see that this does not scale. If you have a very, very large network, you may not want that every BGP router speaks to the n-1 other BGP routers. We will see that there are optimizations that can be done to avoid that. But for the moment, let's keep in mind this mental model that every BGP router inside the domain speaks to all other BGP routers. A few questions to check your understanding. And the correct answer is A. Two BGP routers must be connected by TCP connection. So this is true over an external interface, like A and C, or over the IBGP mesh inside a domain, like C and E, C and F, C and D. They have a TCP connection. Do they have to be on-link? On-link means on the same local area network, in the same subnetwork. This is usually true for routers that are external peers. You pull a link between the two, and then they are on the same links in the same subnet, or at least they have one interface that is on the same subnet. It may or may not be true for BGP routers that are inside the same network. If the network is large, this will not be true for most pairs of network, like C and F are not on-linked. To go from C to F, you must go via one intermediate hop, which may be R or E or D, as computed by OSPF or the interior routing protocol. Another question? So the correct answer is D. So 1 and 2 can be sent, but 3 not. What are those messages? So the first message, C to A. So C is here, C to A. This is C informing A of a path D3, D2X to N1. N1 is a prefix, so how was that known to C? Well, this path was coming here via D2, so B has informed D of the path D2X N1. D has informed C of this path, so this was over eBGP, this one is over iBGP, and C can inform A, which is normal. This is the way messages are propagated, with this the way BGP information can go beyond one AS. The information has come through eBGP, iBGP, and eBGP. D to E. So D to E, well, this here is this message, this path, this is route to the prefix N1, was learned by D from B. And then the rule is that you have to propagate this to all your BGP peers inside the BGP mesh. So B will repeat that information to C, to E, and to F. So this is D repeating to E. Now C to E, this is the same information. So this is not allowed. This is the rule that we do not repeat information that we have learned inside the domain, in the BGP mesh. We don't repeat it inside the domain, because there is, in principle, no need for that. Because there is another rule that says that it's a mesh. So E has learned this information directly from D. D is the source of this information in this domain, so E will learn it from the source. C has learned it also, but there's no need repeating it. So we don't do gossiping like we do in OSPF. The information is learned only once and repeated only when it needs to be repeated. So we have started actually looking already a bit at the mechanic of how BGP is working. Let's return to the fundamentals, why BGP is the way it is, and one of the reasons is policy routing. So what is policy routing? Well, policy has to do with how the interconnection occurs inside the internet. Essentially, there are two types of connections of economical relations between domains in the internet. They can either be peers, in which case that means they agree to communicate with each other, or they can have a customer-provider relation. Somebody is selling service to someone else. Switch is an operator like Swisscom, and it is selling service to EPFL. So EPFL is a customer of Switch. Switch is a provider to Switch. They are not peers. EPFL pays to Switch to get access to the internet. AT&T is a global network operator. Orange is another global network operator. Deutsche Telekom is yet another one. When they connect to each other, they are peers. AT&T is not providing service to Deutsche Telekom, and vice versa. So they are peers. They agree to exchange traffic to make everybody happy, to make their customers happy, because there are Deutsche Telekom customers who would like to access content that is available via AT&T and vice versa. So those are peers versus customer provider. That's the first thing to remember. Let's see what are the implications. Here I'm showing three of those internet giant providers like AT&T, Deutsche Telekom, and Orange, if you want. And they have customers. They have their own customers here. And of course, they connect to each other to provide full connectivity and to provide service to their customers here. Now, there is a tricky thing. Assume this connection between ISP3 and ISP1 is a local one, perhaps in North America. ISP2, ISP1 connection here is a local one in Europe, and ISP2, ISP3 have an interconnection which is over a transatlantic link. Then it would be advantageous for this guy, ISP3, to send the traffic, for example, its own traffic, or traffic coming from its customers, to the customers of ISP2. The normal thing to do would be to use the link between the two. But a transatlantic link costs a lot of money. If there's a lot of traffic in it, you will need a bigger link, so you will pay more. So one thing that may be tempting is to minimize the amount of traffic by saying, after all, ISP1, let me push the problem to ISP1 that happens to have good connectivity in various places of the world. So it's tempting for ISP3 to send all its traffic to Europe to ISP1 that will then connect to ISP2. Right. But if this is accepted, ISP1 is in fact providing a transit service to ISP3. It is saving to ISP3 the money of this transatlantic link. If ISP1 accepts to do that, probably he would like to have ISP3 as a customer, not as a peer. So if they are peers, you don't want to do this. The goal of policy routing is to compute routes and distribute routes such that what happens is really what the different actors want. For example, in this case, ISP1 does not want to serve traffic from C3 to C2. To this end, a common rule that is used practically by all ISPs is this one. You propagate only routes that come from customers and not, routes that come from peers and providers are not propagated to peers and providers. So you propagate routes. Routes can come from peers or providers or from customers. The route that comes from customers, you propagate them to everyone. The routes that come from peers, you propagate them to your customers, but not to your peers. Concretely, this means if I zoom on ISP1, ISP1 receives from ISP2 this route, ISP2, C2, N2. So this is, ISP2 is informing the rest of the world where and how to reach N2, which is the job of ISP2 because N2 is a customer of ISP2. ISP1 receives this route from a peer. So it will propagate it to its own customers, but not to other peers like ISP3. So ISP3 will not know that ISP1 has a way to reach N2, will not know how to reach N2 by going through ISP1, so ISP3 will not send traffic to ISP1. In contrast, C1 will know and will go via ISP1, but this is the job of ISP1, it's receiving money from C1 to transit traffic. So this is how things are desirable. This is implemented, we will see, by a combination of what we will call the decision process and import and export rules. In the lab, you will see things like route map, and in the course, we will talk about the decision process. Little quiz. Assume now this link does not exist. The ISP1, the ISP2, ISP3 link does not exist. Right? What will happen? Well, nothing great will happen. It won't work, right? By the discussion we've seen before, right? What are the implications of this? Right? Well, if you are two ISPs like 2 and 3, and you don't connect directly to each other, you're stuck. So the practical implication is that the internet, I said, is self-organized, but the result of the self-organization is the emergence of giant operators. They're called the tier 1 operators that are like the 3 ISPs shown in this figure. And those operators must connect to each other because none of them agrees to transit for the others. So we must have full connectivity from all tier 1 operators to all tier 1 operators, and this is how the internet is organized today. So at the top of the internet, you have around 10 so-called backbone operators or tier 1 operators that each connect to everyone, and they are really the backbone of the internet. Anybody who is not one of them has to connect to one of them as a customer, has to pay to them. This has emerged over the years. There's no formal rule. This is just the result of business relationship by having other operators like Swisscom try perhaps to do the same, realize they're too small, it would cost them too much to be able to connect to everywhere. So at the end, you do an economical optimization. Is it better to pay a contract to AT&T, Orange, Deutsche Telekom, so that they serve my traffic if I am Swisscom, or should I try to become one of those global operators? So we have seen at the higher level how the internet is organized using BGP. What we will do now is dive through several steps into how this is done concretely so that you can manipulate things in the labs. First things that you will see easily in the lab is that BGP tries to be not too verbose. Question?
Excuse me, before we continue, I just wanted to ask, for example, the IPs which stand behind sites like Google.com, they also have some internet service providers here, right? Like, or they somehow personally connect to this like backbone network.
So which?
The question is, for example, Google.com, it is also served with a usual internet service provider as we serve, right? Mm-hmm. Yes?
So what is Google Home?
The question is, like, when I connect to the internet from home,
yes.
I have my ISP.
Yes.
When Google.com wants to...
Or Google Chrome.
Google.com.
Yeah. Okay.
So Google.com also has some ISPs, right?
Google has its own part of the internet, correct. So it's one of those domains. Google is one of those domains, but it's not a tier. So the question is what happens with Google, which is a large fraction of the volume of the internet. It's not a tier 1 internet service provider. It's not one of those global things in the sense that you cannot obtain from Google service provision. If tomorrow you decide to provide internet service in your neighborhood, for example, to compete with Swisscom and Sunrise and the others, you cannot go to Google to get global connectivity. They are not in that business today. I'm sure they would love to, and they will try one day to, because if they also own the internet, then they can have more control. But today, they are not. So Google connects to internet service providers for their customers, but for their own infrastructure, they run their own internet and they don't rely on internet service providers. But from home, when you access YouTube, you go via Swisscom or Sunrise or Cablecom, something like this. That peers with another network, perhaps Orange or Deutsche Telekom, that eventually peers also with Google. So about the BGP protocol itself, BGP tries to minimize, BGP has to do a much more complex job than all other routing protocols, because things cannot be aggregated by computing shortest path, for example. We need to have the complete information. So BGP information is fairly large. It's a big database, although it's not structured as a database, but simply a big table, but it has a lot of information, as we will see. So it tries to be as silent as possible. So it doesn't periodically repeat messages. It simply will inform the modifications. So when two BGP routers connect, of course, at the beginning, they're a bit like OSPF, they have to synchronize to send all the information that they have, and then they will send only the updates, which are addition or deletion. So if a route is removed, you can also inform your neighbor that the route is removed here. That is more efficient than counting on timing out, for example. Of course, there's also keep alive mechanisms, as usual, to know whether two BGP routers are still alive. So when they speak together, they send a heartbeat message so that you can detect failures. That's the usual stuff we have seen everywhere. The mental model of a BGP router is this one, in fact. It's a mental model, so in practice, everything is often written in one big table, but mentally we can think as this way. A BGP router keeps separate tables for what has come in, what has come out, and the result of its decision. So what has come in is a copy of all the messages it has received from all its BGP peers. So when router A informs router B of something, B receives that information and keeps it. Then the so-called BGP decision process will compare all the information it has about a route. Very often, there will be multiple routes. As you can imagine, all the tier 1 operators are connected to each other, so there's lots of multiple routes to one given destination. BGP selects one. That's one rule of BGP. The BGP decision process selects one route. Not like OSPF that allows equal cost multipath routes. BGP never does that. It selects only one route. That's the first rule here. Then, having selected a route, it will inform its neighbors. If the policy allows it, you may refuse to inform a neighbor, as we have seen. So you may apply export policy, and you send that to your neighbors, and you keep that in a local buffer because it may take some time to transmit it. As we will see, the main interesting thing is here on the inside. This is called RIB-in, Routing Information Base, in because it's the inside, the incoming information. Since BGP keeps only one route, it is still useful to remember the other alternatives. In particular, if there is a failure, assume you're a BGP router, you've received many possible routes to a destination, you've kept one, but the router that had advertised this one is dead. So this route is no longer valid for you. Then you can very quickly find a new route by simply looking in your local database, what are all the other routes that existed that you had not chosen before because they were less good, but they may become better now because the best one has disappeared. So the rule is BGP picks only one route, but is smart enough to remember the ones it has not preferred. And the other rule is you can export only the routes that you prefer. So if there are many routes that are possible to you, you will not export all those many routes. There's a very good reason for that. It is simply the exponential growth that there would be. If for every route, for every possible destination, you have 100 possible routes, and you inform all your neighbors of the 100 possible choices, they will combine that with the other 100 possibilities they have, and after a few hops in the AS chain, you will have an astronomical number. So to kill this, you export only one route. The routes are the records that are kept in the routing information base of BGP, which contains obviously the destination network, and all the other information. We've seen part of it, which is the AS path, the collection of all ASs that you have to go through to get to the destination, and a number of attributes. There's, in practice, up to 100 possible attributes. We will see a few of them. They are essentially priority things, because when BGP selects a route, it's not doing like OSPF, shortest path, or others, or we have seen in SDN. The problem is similar to what we have seen in SDN. You may have multiple routes to a given destination, and then to choose from them, you use a combination of weights and priorities that we will see in detail in a few minutes. The decision process that has to apply those priorities is the key part of BGP, and by default, for example, on Cisco routers, here is what it does. It looks at all routes and screens all those attributes in this order and picks whatever is best. For example, if, let's ignore number 1 to, no, let's look at number 0. The weight is a priority field that is put on the route when the route comes. So using a program of using a configuration that you do on your router, you may decide all the routes that come from Swisscom, you like them very much, so you put a very high weight. All the routes that come from Sunrise, you don't like them, you put them a very little weight. So you can do that locally, and then the decision process will use those weights if there are competing routes to choose whatever is best. It uses a number of criterions. Weights and local preference are priority fields that we will discuss a bit more later. AS path we have seen. So we see that if local pref and weight are not used, the first thing that a BGP router will do is give priority to the route that has the shortest AS path, like I have illustrated a few minutes ago in an example. And then if all those criterions are the same, you go into the list. We see, for example, here one criterion, eBGP is better than iBGP, means that if all other criterions are the same, you have two routes, one that you have learned from the outside, from eBGP, and one that you've learned from the inside, you prefer the one you have learned from the outside. We will see, because this is fresh information. We will see the implications of this on a few examples. So here are two fundamental examples where we do the anatomy of what BGP routers do. Of course, in reality, things are much more complex. BGP routers in the internet today manipulate close to a fraction of a million, half to a million routes. So they do that for 500,000 times. We will do it for just a few routes here. I'm showing two autonomous systems, X and Y. Each of them has two routers, and we have two pairs of BGP external peers. R3 is peer with R1, R4 with R2, and we focus on R1 and on the ASX. So R1 is connected to R2 by an iBGP peering, means there is a TCP connection between the two. And we'll show what happens in R1. So let me assume that R3, which is connected to this network prefix, R4 also, and the domain Y is configured such that both R3 and R4 tell the rest of the world of those two prefixes. We will see how this is done, but let's assume they are configured. You can always configure them manually, as we will see also in the lab. So R3 is instructed to pass the information, so it passes it to R1. So R1 receives from R3 the information, this prefix, and the AS path is Y only. So what will R3 do? Well, it will, so what will R1 do? It will keep them, those two information in its database, incoming database, RIB-in, and it will choose a best, which is the best. Now, the rule is you need to choose only one for every destination prefix. For every destination prefix, there's only one. Now, there's no choice. If the policy allows it, now there might be filtering rules on the input, there might be filtering rule in the decision process that forbid to receive routes from Y. We assume it's not the case here. So those two routes are selected. They are the best routes. They are the routes that this router R1 keeps. And hopefully will put into its forwarding table, as we will see. Now, the job of R1 is also to repeat that inside the IBGP mesh, so it will inform R2 of those two things. And we'll see that the route contains the destination prefix, the AS path, and an attribute that is always present is the next hop. Next hop is an IP address, IPv4 or IPv6, depending on whether BGP can be used for both IPv4 and IPv6, so both will be present. It is the IP address it's an IP address that's inside my domain, and that corresponds to who gave to me this information. In this case, it is the address of a router R3. Now you will tell me R3 is not in my domain, but BGP considers that the links that are at the boundary, they must be visible inside the domain. Concretely, inside the domain X, we must know how to route to this prefix, 1112. So this is a shared link. So this shared link must be present in both domains, in fact. And the next hop we see is the address of R3, the interface of R3, that has sent this information to R1. So this is propagated everywhere. We will see that we need that information to know what to do with this route information. So this information is passed to R2. That is step 1. Step 2, now assume that R2 has received the same at about the same time from R4, and R2 does the same job. So R2 now repeats to R1 the information it has received from X. So the first thing R1 does is like a hamster. It keeps every information it has heard. So it will keep in its database this new information. What's the difference between this and the previous? Well, it's only the next hop. We see that in BGP there is no distance to destination. There is only a path. The paths are the same. The only difference is the next hop. Another difference is that R2 is an IBGP peer to R3. To R1, whereas R3 is an eBGP peer. So this is what is here. Now, before we do the break, quick question. Which of the two routes will R1 select? Will they be selected? Right. So now there's a concrete problem. If we look at destination 10.1, we have two routes. So BGP has to choose one of the two. Which one will it choose? And the correct answer is D. What will happen, in fact, well, we apply the decision process. The decision process says you go through a number of things, local pref, wait, local pref, AS path, they're all the same here. Local pref and wait are absent. So the next criterion is, does the route come from eBGP or IBGP? And here, the red route comes from IBGP. The gray one comes from eBGP. So this is fresh information. This is second-hand information. Here, the default rules of BGP say you prefer the fresh information, which means this information is preferred. So as a result, there is no change. The best route remains this one. None of those will be promoted to best, which means, in practice, that R1 prefers the information it has received here, right? Similarly, R2 prefers the information it has here, which means that whenever R1 has something to route to a prefix 10.1 or 10.2, it will consider that the next hop is via this link. So R1 wants to always send via this link. Voilà, we'll see the implications of this in a few more minutes. We do a break and resume in 12 minutes.